David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with notes or write down some questions. Third, you can turn on the captions and read my words on the screen. This video covers the second half of the IB Applications and Interpretations, Chapter 7, Probability. This section covers probability distributions, which is a little bit more complex. I want to say one thing, or 2 things. I'm going to put links to all the individual videos upon which this video is based, so you can always dive down in there for a more thorough treatment of any of the given topics along here, and example problems. I'm not going to spend a lot of time doing example problems on this video, otherwise it would be way too long. The other thing is watching this video alone does not prepare you for our unit test. You need to do the practice problems. Super, super important. Okay, let's get started. So 7i was an introduction to random variables. And these problems do get more abstract, but they also are anchored in reality. And they would help us answer the question like this. If I flip a coin 10 times, what's the probability I would get 8 heads in those 10 flips? And the thing is that it's complicated because there's a lot of different ways to get 8 heads in 10 flips. There's not just 8 ways. There's a lot more than that. So what we need to do is we need to use all kinds of different tricks to calculate probabilities for situations like that. So let's take a look. These are variables that change according to chance. Okay, so the outcomes based on the variables are governed by probability. Now check this out. They're discrete, so they can be found by counting. So typically what we're looking for is a success. Did we get ahead or not? So a success or a failure. So outcomes are measured by successes or failures. Finally, the probability distribution shows all the outcomes with their individual probabilities. And we're going to make a table to show that. Okay, we're going to do a bunch of things with this example. So check this one out. This is a probability distribution. And we have a pretty abstract event. I'm not telling you what's happening, okay? But I'm telling you my outcomes. My outcome could be a 3, 4, 6, 9, 10, or 12. This could be a weird die, a 6-sided die that's not fair because these probabilities are all different. But it could be anything. It could be just a button that you press and it spits out one of these numbers. So I'm also telling you, so that's the random variable x, uppercase X. And now the probability that uppercase X equals little x means that the probability that we get a 3 is 0.2. Probability that we get a 4 is 0.15, 6, and so on. So that gives us the probabilities of all of our outcomes. What you say? What's K? How do we know what K is? Pause the video and think real quick. Okay, K has to be 1 minus all of these added up because all of these have to add up to 1. So K is 0.05. Okay, so great, we're good to go. So now all of these things add up to 1. So now we can start calculating some probabilities. Okay, 2 quick calculations. I'm going to tell you what to do. Pause the video and do it. Probability that x is greater than or equal to 6. You just add up all those probabilities. That will give you that probability. The probability that x is between 4 and 10, same thing. Add up all those probabilities and then put that there. And I'm going to make it just a little more difficult. We're going to take that off of there. Okay, pause the video, do both those, come right back. Okay, so all I did is I just used my table with my my outcomes and their probability of success. I wrote them down just so you could see that, added them up. So there's a 65% chance that x is going to be greater than 6, and there's a 60% chance that x will be greater than or equal to 4, but less than 10. One more example with these types of calculations. What I want you to do is figure out what is the probability that x is greater than or equal to 6, given that x is less than 10. Now think back. Remember, there's a nice easy formula that you can plug that in and figure this one out. All right, so from our formula, from our rules, this is actually the last review video because this was in the sort of what I'm calling the straight up probability. To get the conditional probability, it's the intersection of the two on the top of the fraction divided by the given that condition there. So I went ahead and sketched this out. I'd like you to pause the video and do that calculation. So what I did is the intersection is the probability where it satisfies both, greater than or equal to 6 and less than 10. And that really is just here, less than 10, but greater than or equal to 6. So that's 0.45. The probability that it's less than 10 is all of those. Okay, so the probability that it's 10 or greater is 0.2, so less than 10 has to be 0.8, and then I divided through and I got 0.563 or 56.3%. 7J covers expected value. And what that is that's a calculation that is kind of like a long-term average. So if we ran this experiment, we pushed this button on the machine and we wrote down all the numbers we got out, we did 1,000 of those trials, and then we added them up and divided by 1,000, that would be the average result. And that's also called the expected result. Now, expected, you won't see them as an actual number because it's going to be somewhere in this range of numbers, but it's not going to be a discrete integer. So let's do that. This is expected of x, big X. So what is the expected value of big X? So really all we do, it's pretty straightforward, is we calculate the probability of each item. Okay, so we multiply down and then we add across. So if you're feeling bold, go ahead and pause the video and do just that. All right, so I multiplied down, I got all these decimals. These are just the individual probability of each of those outcomes. I added them up and I got 7.4. So that's the expected outcome of doing this one time. Obviously, you're not going to get a 7.4. You don't even have a 7 on here. So this is more of a theoretical, like I said before, this is the long-term average for this probability distribution. Before we go on, I just want to make one comment. The kinds of calculations we did in this lesson were complicated. They had a lot of variables. You had to solve an equation to find out your k-value, and then use your k-value to figure out the probabilities, and then go from there to figure out your expected value. Now that's all in the video for 7J, linked below. If you feel like you should review that, take a look at that. If you're in my class, you have notes from that, you might look over those. So I'm going to move us on to our next lesson. All right, the binomial distribution is very interesting if you're a math geek like me. It's a super cool thing that helps us figure out all kinds of interesting probabilities. So the first part of this is about combinatorics, which is sort of like the how many ways can you get 2 successes out of 5 tries, or things like that. So here's an example that helps us calculate the combinatorics thought. How many ways can we get 6 heads in 10 coin flips? Where we're going is what is the probability that we'll get 6 heads in coin flips. But we need to do the combinatorics part first because that's part of our equation. So here's some notation. We use this C for combinatorics. There's a bunch of different ways to do this, but basically what you've got is you've got 10 trials, you're looking for 6 successes. I think in class we also just did it this way, 10-6 with no line. It's not a fraction, it's just 10-6. So the way that works, and this formula is in your formula booklet, the combinatorics for this, 10 trials, 6 successes, is just 10 factorial over 6 factorial times 4 factorial. And this is, what we have here is we have NR. So N is the number of trials, R is the number of successes. And that's going to show up in our formula in a minute. So if you're feeling bold, pause the video and do that calculation. Now that we've got the combinatorics out of the way, let's take a look at the overall calculation. Here's our prompt. What is the probability of getting 6 heads in 10 coin flips? Here's the notation. Random variable x is a part of a binomial distribution. Number n is the number of trials. P is the probability of success. So here's our notation for that, and here's our formula. Check this out. probability that little x equals r. Little r is the number of successes. Here's our combinatorics term. We know that's 210 n r. Probability of success to the r, 1 minus the probability of success, which is the probability of failure, to the n minus r. So go ahead, pause the video, and do a plug-in step with our scenario using this formula. Okay, when I do this calculation, I end up with this plug-in step, and I can do this on my scientific calculator, and I get 20.5%. Now remember, you can do this on your calculator with the binomial PDF function, and it will just do it for you. You just have to enter in your trials, your probability of success, and then the number of successes that you're after. And the calculator will do that all for you. But you may be in a position where you can't use a calculator, and this is not terribly hard to do. Or actually, you may be in a position where you only have a scientific calculator and not a fancy schmancy graphing calculator. You might also get a calculation like this. Find the probability that little x is less than or equal to 2. Now, you could do this in a manual way by adding up the probability that it's 2, that it's 1, and that it's 0. That's a lot of board work. Your calculator will do that with binomial CDF. That's the function. So if you want a little extra practice, go ahead and do that on this problem. When I get that, I get 0.055 or 5.5%. And that makes sense. 10 flips, getting 2 or less is kind of hard to do that when it's always a 50-50 chance that you're going to get heads. So there's that calc. Okay, lesson 7L dealt with expected value, which you saw a little peek about just a few boards ago, and variance. Okay, so remember, variance is standard deviation squared. It gets a little tricky at times. So here's our two equations. Expected value, we already know that. It's the number of trials times the probability of success. There's our expected value. Our variance for random variable x is similar, but you just add this 1 minus p to the multiplication. So really we have the number of trials times the probability of success times the probability of failure. Cool. Okay, so now let's do a problem. Now this one is 100% abstract. We don't know what the scenario is. We just know that random variable x is part of a binomial distribution. We have 10 trials and we have 0.35 chance of success. That's it. So you should be able to do these two calculations nice and quick. Find the expected value of x and the variance of x. So really quick calc. Expected value is 3.5 and the variance is 2.275. Now, if you needed the standard deviation for this example, you would just take the square root of that, and that would be your sigma. 7M covered the normal distribution. This was the start of dealing with the normal distribution. And I find this pretty cool because the normal distribution is out there. If you take some event that's governed by probability, where you have probability of success, and you run many trials, and you graph the number of successes, basically you're going to get a bell-shaped curve. And this is just the property of a normal distribution. And it's out there in the world. This is not something that mathematics has invented to inflict on teenagers. So check this out. It's a bell-shaped curve. It's symmetrical about the mean, so the curve is the same shape going either way from the mean, which is right here. We use mu for mean, and the mean is the same as the median, is the same as the mode. So another way to say it is the average is the same as the most frequent number, is the same as the middle number. So all three of those are the same. Now here is an attribute that you should know about a normal distribution. 68.3% is within one standard deviation of the mean. So that's negative sigma. Remember, sigma is our Greek letter for standard deviation. So between negative sigma and positive sigma, 68% of the data lies in that zone. Similarly, within two standard deviations, we bump that up to 95.5% of the data. So with a normal distribution, just about all the data is within two standard deviations of the mean. And that gets almost complete with three standard deviations, because then we're at 99.7%. And we had some problems, or maybe we'll do one in a minute, where you had to use this understanding to answer a probability question, sort of like a without a calculator type question. Now, I know you guys are in applications and interpretations, so that means that you're going to be able to use your calculator for everything, but don't underestimate the IB's ability to ask you a thinking question that would require that you remember this information, which is not in your formula booklet. Okay, a quick prompt to make a sketch of a normal distribution, and that you very much might see on an IB test. So here is our notation for our normal distribution. Random variable x is part of a normal distribution, that's the n. And the two parameters in here are not the same as the binomial. Remember, binomial was trials, probability of success. In a normal distribution, this number is the mean, or mu, and this number is standard deviation squared, or variance. So here's our problem. Random variable q, part of a normal distribution. 7.5 is the mean, and the variance is 2.5 squared. What I want you to do is sketch that distribution and show two standard deviations on either side of the mean. Okay, we are in the middle of a thunderstorm here in Sedona, Arizona, and the power just went out. So I'm going to keep on shooting, keep on going. Hopefully it's not too dim, and be ready. The power may come back on and the lights will come back up, so we'll see what happens. So here's my sketch. I made my axes and my bell-shaped curve. Make your curve first. Don't scale your axis first, because then you've got a tough job of drawing your curve so it works right. So I drew my curve, and then I put my mu, my mean is 7.5, and then I scaled two standard deviations in either direction, and I sketched my normal distribution. Okay, here's a prompt. Find the probability that random variable q is less than 5. Now, this is a no calculator question. Now, of course, you can put that in your fancy calculator and have it tell you what the probability is. But again, I might be able to write a question that requires that you understand how to use this graph to show what that probability would be. So, if you're feeling bold, pause the video and do that. I'm going to walk you through it. So, get out my red pen, and what we're going to do is we're going to shade the area that satisfies the condition. So q less than 5, that's here. So that's all of this area. Just as a reminder, we didn't talk about that in the last board when we talked about the normal distribution, is that the entire area under the curve is equal to 1. And that's basically very analogous to the probability, all the probabilities for a given situation. Also, add up to 1. Okay, so now that I've shaded that, we can figure out what the probability is. Pause the video if you haven't already done so, and do that. All right, so check this out. Knowing what I know about where the data is, I can just do this graphically with thinking instead of my calculator. I did this question on the calculator as well, and I got the same answer I got this way. So good to go. So check this out. We know that 50% of the data is on the left side of the mean. So that's 50. We know what we want is from 5 or less. So that's from 1 standard deviation that way. So whatever this is q is less than 5. That's what we're after. So what I did is I figured out what this blue stuff was, so I could subtract it from 50, leaving me with whatever that is. Now the blue stuff, from here to here is 68.3. The curve is symmetrical. So this is half of 68.3. So I went ahead and divided through, and I got this blue area is 34.15. So the probability that q is less than 5 is 50 minus 34.15, or 15.9%. Woohoo! Okay, students asked me, when do I use binomial? When do I use the normal distribution? How do I do that? What functions on my calculator do I need to do that? So this board is intended to kind of orientate you to all of that stuff. So first off, binomial, normal, okay? When do you use which one? So a binomial distribution will do a probability calculation where the situation has trials. So flipping a coin multiple times. If you flip it 10 coin times, you have 10 trials. So that would be a binomial distribution problem. Normal distribution situation has one event. So you're just doing one thing one time and you're trying to figure out the probability. So that's the big dividing line between the binomial and the normal. Now, we have 4 calculator functions that will help you do this. So for the binomial distribution, there's binom PDF and binom CDF. PDF is for one outcome. So for example, the probability of 2 successes, random variable equals 2, so 2 successes. Binom CDF is what you use when you want to calculate a range of successes. So this would be for x being less than or equal to 3 successes. So instead of doing 3, 2, 1, and 0 successes, 4 calculations, binom CDF will do it all at once. You just have to put the parameters in correctly. And a note, between the 2 calculators that I support in my class are the TI Inspire and the TI 84. The TI 84 only lets you do the left side of the distribution. So if you're calculating the probability for the right side, you need to convert that to a left side probability to calculate and then subtract your result from 1. So it's a little extra critical thinking step if you're using the TI 84. Now, on the normal distribution, same thing. PDF is for one outcome, CDF is for a range of outcomes. And the same caveat with the 84 with a range. You have to be careful about how you enter that in to your calculator. Okay, 7N, last lesson in this fairly long chapter. Fortunately, not terribly complicated. Okay, so inverse normal. Up until now, we've found probabilities with the normal distribution. You're given parameters and you're asked to find probabilities for various levels of success. So this is backwards. We're going to give you a probability and a parameter, i.e. the standard deviation and the mean. We'll give you those 2 parameters, and we're going to ask you to come up with some of the numbers that you would normally be given. So here is an example problem that you might see. Heights of trees in the redwood forest have a mean of 280 feet with a standard deviation of 32 feet. Now that might be close to reality. I'm not sure, I just made those numbers up. So the Forest Service wants to track the tallest 10% of the trees. So they want the highest 10% of the trees, they're going to track them, and they're going to do their scientific thing with that. So what we need to know is what is the minimum tree height for them to have to track. So we have a probability, we're looking for a height that above which is going to include the 10% tallest trees. So I would say pause the video and draw a normal distribution with this information and shade the area that you need and the number that you need to find. Okay, here's my curve, my bell curve. Made my top here, there's my mean, and then 1 standard deviation. I'm just adding and subtracting 32 from each of the numbers as we go out. So that's 1 standard deviation away, and that's 2. Now, the trick is you need to figure out where that value is, that tree height. Remember, these are all tree heights. What is that tree height that's going to make 10% that way? So pause the video for a sec and see if you can figure that out. So I did a little critical thinking. I need to figure out where to place my A, and I put it right there. That's my number that I'm trying to find. What I know is that between 1 standard deviation, this is 68.3% of the data. So I need to find out what these chunks are so I can tell whether or not my A is going to be in here or here. So check this out. I subtracted 68.3 from 100. That gave me this amount, or I'm sorry, that gave me this plus that. If 68.3 is here, whatever's left is in both those areas. So I divided it by 2 so that I could get what was here. So 15.85 standard deviation lies on the large side to the right, 1 standard deviation and further from the mean. So I know that. So I'm looking for the top 10%. The top 15% start there. So I know my A, whatever that number is, whatever that tree height above which I've got the tallest 10%, that's right there. So now we just do our inverse normal calculation. Okay, I've formalized what we're asking for in my probability statement. So here we go. probability that the random variable x is greater than a. We know it equals 0.10. We just don't know what a is. So I put that in my calculator and I get 321 feet. So all the trees that are 321 and higher, those are in the top 10% of tree heights in the forest, and these are the heights above which the Forest Service should track. Now, let's take a look at the calculator function. It's INV norm for inverse normal, and you're just going to have to enter the area / probability. So area, because it's area under the curve, right? We're figuring out this area right there. That actually we knew the area. This was 0.1 or 10%. So you're going to have to enter that. You're going to have to enter the mean, which we were given. You're going to have to enter the standard deviation, which we were given. And then you're going to have to tell it which direction, which side, the bound or the direction, because there's a similar A for this side. So you need to tell your calculator, what am I looking for? Am I going to the right or am I going to the left? And once you put that in, you just press enter, and that's what you get. Now that you've watched the video, take a minute to jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch portions of the video that were a little bit challenging the first time. If you enjoyed the video, please click like. And if you'd like to help me grow my YouTube channel, please click subscribe.